All right, so we're going to do problem 27. So this is the diagram for 27. You have object A, so this is the object A. So A and B. And object A has weight that's 102 Newton, and body B weighs 32 Newton. The coefficients of friction are given, so the static friction is 0.56, and the coefficient of the kinetic friction is 0.25, and the angle is 40 degrees. Now, in the problem it says, let the positive direction of an x-axis be up the incline. And in unit vector notation, you're asked to find the acceleration of object A if it's part A when it is at rest, when it's not moving, and when it is moving up, and for part C that's moving down. So let's do part A first, when it's not moving. What does that mean when it's not moving? When it's not moving, it means that it's the static friction, the static friction acting on the object is balancing the horizontal forces on this object. So what we need to do first is to draw a free body diagram. And so let's draw our reference axis. So this is your horizontal axis. So that's your x. And the vertical direction is your y. Okay? Now let's see how many forces acting on object A. So this is the point where the object is. And it has weight, so that's called that WA. And then there's a normal force that's pointing in this direction. And there's a tension, so the tension is right here. So that's your tension, okay? And because it's not, so if the so let's assume so if it is not moving, which means that we assume that the frictional force, so it has it is pointing. Let's say if we assume that is it has the inclination to attempt to move upward because of the presence of the tension. If we assume that it is moving upwards, and so if it's moving upward, which means that the friction force has to be downward to balance the attempted motion. So we assume that it is moving upward, and then if after we've done the calculation, if the force happens to be negative, it just means that it is pointing in the opposite direction of what we assumed. Okay, so let's say if we assume that the whole thing is moving up, attempted to move up, because the whole thing is initially not moving. So attempted to move up, which means that the friction and it's not moving, so it's a static friction. Okay, so all these forces have to be balanced because it's not moving. And for this object B, so you have the tension and you have the weight of the object. Okay, and because it's not moving, which means that these two forces have to be balanced each other. And likewise, the horizontal forces along this direction and the vertical forces along that direction have to be balanced as well. Okay, so we can set the equation. So let's set the equation for block A first. So we have the tensions going this direction, we have the static frictions going that way, and we have the gravity that's going that way. So for gravity, because it's pointing downward, so you have a component that's going down, and you have the downward x component as well. And this is your angle theta here. Okay. So, just by looking at this diagram, we can see that the net force in the horizontal direction has to be 0. So from this, we can see that your tension minus the frictional force, which is Fs, minus the component of gravity, which is Wa, and then opposite the angle, so that's sine. So minus Wa, and then sine theta, the whole thing is 0. Okay, we can set the same equation to find out our y component, because the y component, when you add up all the components, they should balance each other as well. So your y component, you have an upward normal force, you have the downward gravitational force along this axis. So you have your n minus Wa, and then this is adjacent to the angle, so that's your cosine theta times cosine theta. The whole thing is equal to 0. Okay, so in that case, so we have our normal force, which is just Wa cosine theta. Your Wa is 102 cosine of the angle 40 degrees. So we can quickly calculate the numerical value for the normal force. So the normal force we have, I did not calculate this value. So you have a normal force right there, okay? And you can calculate, so you have that, but we have that expression. So your N is equal to 102 times cosine 40 degrees. And tension is equal to this. So you're asked to find the tension, the static friction. In order to find that, you need the information of the tension. So how do we find tension? If we look at this, tension and this way have to be balanced each other. So you can set it that T minus WB has to be equal to 0, which means that your tension value is just the weight of this block B. So it's 32 Newton. And then after you have that, then we'll plug into this equation. So you have your Fs and rearrange that. So you have your 32 minus the frictional force, which is static because it's not moving. The minus WA sine theta. WA is 102, and then sine of 40 degrees. And the whole thing is equal to 0 based on this equation. So your Fs, your static friction, after you do the calculation, you found that your Fs is actually equal to negative 33.56 Newton. So what does that mean? It means that this frictional force has this magnitude, 33.56 Newton, but then it is pointing, instead of moving, pointing downward, the actual direction is actually pointing upward. Okay, because we assume that the friction force is downward, but then we calculate that to be a negative value. It means that the friction force is pointing in the opposite direction. So you got the 33.56 Newton. Okay, so this is a static friction. So with this static friction, which is 33.56, we can actually compare this static friction to the maximum static friction to see if if that's still under the maximum static friction. Okay, so we can do the calculation. So the maximum static friction is equal to mu s times the normal force. So your mu s is 0.56, and then the normal force is this expression, which is 102 times cosine 40. So when you plug in numbers, you'll find that the maximum static friction has a magnitude of 43.75 Newton. What does that mean? It means that the static friction is still less than the maximum static friction. If it's still less, if this force is still less than the maximum static friction, it just means that the whole thing was remain remain at rest. It will not move. It will not move up or down. Okay, so that's your part A, when the object is initially at rest, and then the tension itself is not enough to have it moving. Okay, so that's that. Now for part B, let me just erase the whole thing here. And of course, a free body diagram, we'll probably have to redraw it. All right, so let's remove that. The tension, the gravity, and the normal force will stay the same, but the friction force might not be. Okay, so that's the part B. So for part B, you're asked to find if the A is initially moving up the incline. Okay, so now the whole thing is moving up the incline. When it's moving up, we know that there's a friction force that's in the opposite directions of the motion. So, and because it's moving, which means that now the friction becomes a kinetic friction. So you have the kinetic friction, which is Fk, that's acting in the opposite directions of the motion. So this is a free body diagram for part B. You have the tension, you have the kinetic friction, you have the gravity, you have the normal force, and you still have the block. And now the whole thing, if this is moving up, which means that this has to move down. Okay, what does that mean? It means that there is acceleration. So you don't, you cannot set in, the net force equals to 0. Now it's equal to ma. Okay, so now that's solve the equation. In the vertical, let's look at block A. In the vertical, that is still not the whole force is still balanced because it's not moving in the vertical direction. In the horizontal direction, the net force is in this direction. Okay, so net force in the y direction is equal to the normal force minus the weight of the block A, and then times cosine theta. This whole thing is 0, so your m value is WA and then cosine theta. Now the net force in the y direction, in the x direction, is no longer 0. So that will be the mass of block A and then times the acceleration. Okay. So what is the net force in the horizontal? That will be positive tension, negative frictional force, and then the negative, gravitational force. So you have T minus your Fk, and then minus Wa, and then because this x component is opposite angle, so sine of theta. That's this is the net force in the horizontal direction, and that's equal to the mass of the block A times the acceleration. Okay. Now, if we look at this equation, we can see that tension, we don't know. Acceleration, we don't know. So we have one equation but two unknowns. So you cannot just use this equation to trying to find your tension or the acceleration. What we need to do is that we need to utilize the information from block B. So let's draw a free body diagram on this. So you have the weight of B, you have the tension, and the whole thing is moving down, which means that your WB is going to be greater than the tension, and the net force will give rise to the mass of B, because you're looking at this block, the mass of B times the acceleration. It is the same acceleration because they are moving as a system. Okay. So you can see that this is actually, whenever you're doing incline, you have the two equations, two unknown. You can manipulate the equation. You can add these two equations together. So we can add these two equations together so to eliminate one of the unknown. Okay. So what we have here is that T and T tension get cancelled. So what we have here is the weight of the block B minus frictional force minus weight of block A times sine theta, and the whole thing, when you add this, together, that will be mass A plus mass B, and then times the acceleration. So from here, you can actually calculate the acceleration because your acceleration would just be WB minus FK minus WA sine theta, and then over MA plus MB. So we're ready to plug in the numbers. So your WB is 32, so you have 32, and then minus Fk. What is your Fk? So Fk is mu k times n. So mu k is 0.25, and your n is Wa times cosine theta. Wa is 102, and then your cosine of 40. So you have cosine of 40. So when you plug in a number, your Fk, let me see if I have numerical value. Your Fk, I do not calculate your Fk, but this is your Fk value. Okay, whatever value you plug into there. So here, and then minus Wa, which is 102, and then times sine of 40 over the mass A and mass B. You're given the weight, so the combined, so you add them together divided by 9.8, that gives you the combined mass. So you have 102 plus 32 divided by 9.8 gravity. So your acceleration, after you do the calculation, you should get a value that says negative 3.88 meter per second square. Okay? So you can see that your, so initially it is moving, so this is your acceleration magnitude, that is negative 3.88. So that's your part B. Okay? So now let's moving on to part C. When it's moving down initially. So if it's moving down, this is the directions of motion initially. So it's and then so your Fk will have to change sign because now the motion is downward. So now your Fk is in this direction. So this is your Fk. Okay. So the whole thing, let's see what needs to be modified. The net force in the vertical direction on block A still is 0. So that's how you determine your normal force. So your N is equal to WA cosine theta. You still have your normal force. That's not changing. And then horizontally you have the whole thing. This thing is moving down, which means that this block B is going to move up. Okay, so we can apply Newton's equation according to this diagram. So you have the gravitational force along this along the incline now is greater than the tension and the friction force. So the whole thing is moving down. Initially it says that it's moving down. So that's initially it is moving down. So the friction force experience is this one. So we can find out at that instance what is the acceleration when when it's moving down. So we can have so if this is the leading term, we can have the gravitational force, which is WA, and then times the sine theta, because it's along this horizontal direction. So WA times sine theta. Now we're going to actually use this and then subtract these two forces from this value and set it equal to MA. Okay, so it's minus tension minus Fk, and it's equal to, so this is a net force in the horizontal direction pointing downward, and you have the mass of block A and mass of block A times acceleration of the system. So this is equation according to this diagram. Now, according to this diagram, the whole thing is moving up, which means that tension is going to be greater than the weight of block B. So you have T minus WB, that is equal to mass of block B, and then times the acceleration. So again, we're going to add these equations together to eliminate one of the unknown, which is usually the tension. So tension get canceled. So you have WA sine theta minus WB minus Fk. That's on the left-hand side. On the right-hand side, you add this together. So you have your MA and then plus MB and then times the acceleration. So your acceleration is equal to this. And then over the combined mass. So combined mass, again, is the weight divided by 9.8. So after you do this, you'll find that after you plug in the numbers, you'll find that you have the value that's equal to 1.026 meter per second squared. Okay? So you can see that, so this is basically how you do this kind of problem. In fact, it involves three equations. Two from block A and one from block B, and then you can eliminate tension so that you can find the acceleration. And once you find the acceleration, you can just plug into any one of the equations. You're going to find out how much tension is needed in order for the block to move in a specified direction. Okay, so that's basically problem 27. Like discuss the scenario. It discussed three scenarios: when the block initially is at rest, and then when initially is moving up or initially moving down. You can see that there are signs that you have to pay a particular attention to, so that in order to have all the forces accounted for correctly. Okay, so let's do next one, which is problem 28. And let me just erase this. All right, so problem 28 is in the same diagram. So we still have this, and we have this, we have this. You have A and B. All right, so in this diagram, two blocks are connected over a pulley. The mass of block A is 10 kilograms. 10 kilograms. So MA is 10 kilograms, and then block B, the coefficient of kinetic friction between A and the incline is 0.2. So mu K is 0.2. and the angle is 30 degrees. Okay. Block A slides down the incline at constant speed. So this thing is moving down at constant speed. So now go. Moving down constant speed. Okay. So what is the mass of block B? So this problem tells you that this is, again, a two-block system, and this thing is moving down, which means that this block has to move up, and it's moving at a constant speed, which means that the net force acting on the block has to be 0 because there's no acceleration to change the velocity. So what it means is that the net force, I'm going to use the vector sign, the net force has to be equal to 0. Okay, so under what what is the required mass for that to move at a constant speed? So we're going to draw the free body diagram. Let's draw our x and y axis. This is block A. It has weight. That's called a WA. It has tension. That's pointing in this direction. You have the normal force. That's in that direction. And there's the frictional force because it's moving downward. If it's moving downward, which means that the frictional force has to be up. So you have the frictional force and then it's kinetic friction. So you have the Fk that's acting like that. And this is your angle theta. Okay. After we've done so many incline problems, then solving this kind of problem is really kind of easy because it's kind of the same format. So you have find out all the forces in the vertical. So upward you have the normal force and gravity. Gravity has a component that balances the normal force and has a component that's pointing in that direction. So let's set up the equation. So we have the in the vertical, so the net force in the vertical is equal to 0. So you have the normal force minus WA cosine theta because it's adjacent to the angle that is equal to 0. So that your normal force is equal to let me see if I calculate the numerical value. This is problem 28. So, all right, I don't have that. So your normal force is WA and then cosine theta. Now let's look at the net force in the vertical, in the horizontal. It has to be 0 because the net force, is 0. So you have the tension. You have tension plus the frictional force, and then minus WA, and then sine theta. And so it set it equal to MA. Now it's equal to 0 because it's moving at a constant speed. And the free body diagram for this is that you have the tension that's upward and you have the weight that's downward. So these two have to be balanced. So you have your you have T minus WA that's equal to WB that's equal to 0. So what it means is that the tension is just equal to WB. Okay, so what is our tension value here? And so you can calculate. So we can just replace our the tension with a WB. So you have the MB times G. That's your WB, and then plus mu K, Fk. Your Fk is mu K times the normal force. So you have the mu K. Normal force is equal to mass A times G, and then times cosine theta, and then minus WA, which is MA times G, and then times sine theta. And the whole thing is equal to 0. So there you can figure out what your mass of B is. So because mass of B is just equal to, when you move these two terms to the other side, so you have your MA G sine theta, and then minus mu K MA G cosine theta, and then over the G value. And you can see that your G just get cancelled. So G cancel. So you have your MA sine theta minus mu K MA cosine theta. So you have the mass of A, you have the theta, you have the mu K. So when you plug in, the numbers, you should get a 3.26 value for block B. So that's the answer for that problem. So you can see that this is actually quite straightforward when the whole thing is moving at a constant speed. There's no acceleration. The net force has to be balanced each other. So they just 0, 0, 0. Okay. All right. Now let's see. this one. We're moving on to another problem, that's 29. All right, 29, that says, let me draw the diagram first. So you have your A, you have your C, and then you have your B. Okay, 29. So a box of 29, let's see. Where's 29? So in this diagram, block A and B have weights that are given. So block A has weight, that's 44 Newton, and block B has weight, that's 22 Newton. And determine the minimum weight of block C to keep A from sliding if the frictional force is equal to 0.2. All right, so let's do part A first. So you have this arrangement, and A and B both have weights, and you have a third object that's placed on top of A, and so you're asked to find what is the minimum weight of of block C to keep everything from moving. Okay, so let's say if the block C is not over there, these things will have a tendency to move in the rightward direction. So the attempted motion. So the attempted motion will be to the right. So we know that the static friction has to be opposite the attempted motion that's pointing to the left. Okay, so we can draw a free body diagram just to see what is the so when it's not sliding. So that what is the minimum weight? So it's not sliding. If it's not sliding, it means that the frictional force is basically has to be less or equal to the maximum static friction. Okay, so we can draw a free body diagram on this thing. We treat this as a system. So let me draw the free body diagram here. So this is the combined mass of block A and block C. So you have I'm using the capital to indicate that's the combined mass. So this thing is your mg, okay, and there's an upward force acting on the two blocks, and then you have the tension that is away from the contact point, and then there's a frictional force. So the frictional force will have to be in the opposite direction of the assumed motion. So you have the frictional force, and then in this case, the frictional force has to be equal or less than the maximum static friction. So let's say this is equal to the maximum static friction because you will also find the minimum weight of block C to keep the whole thing not moving. All right. So based on this, we can see that the normal force and the gravitational force that balance each other, and the tension and the maximum static friction, that has to be equal to each other so that the whole thing is not sliding. Okay, and simultaneously your block B, if you draw the free body diagram, you have the mb times g, the weight of the gravitational force on block B, and you have the outward tension. Okay. And if it's not moving, which means that these two has to be balanced each other. So based on this equation, we can set up, we can say that your tension minus the maximum static friction has to be equal to 0. Okay, so your tension is equal to maximum static friction, which is mu s times the normal force. How do you determine the normal force? Normal force minus capital mg is equal to 0, which means that your n is equal to capital G, mg, okay? So when you have this, so what you have here, and then from this diagram, we can see that tension minus the weight of block B is equal to 0. So your tension is equal to this, which are given, okay? So what we have here is that you have the tension, which is the weight of B, which is 22. So you have 22, and that's equal to mu s. Mu s is 0.2, and then times the normal force. The normal force is mg. Okay. So the normal force, let's say, is M and then times G. So from here, G is 9.8. So from here, you can calculate what is the mass. What is the mass? The mass of the combined, combined weight. So let me see. Do I have the mass? This is basically is equal to 0.2 over 22.02, and then times 9.8 here. So you get this total mass. Once you get this total mass, let's see. Are we finding weight or are we finding? Let's see. The weight. Okay, so we want to find the weight. So let's keep the weight. So this is the weight of the block B, which is 22, and this is the weight of the. So that will be the weight. So that's mg. So instead of finding the mass, let's keep it like that. So your mg, which is the weight of the system, is equal to 22 over 0.2. Okay, and this weight is equal to the weight of the block A plus the weight of block C. So this is given. So you can calculate, based on this, you can calculate that the weight of block C is just basically equal to the 110 minus 44. So what is the minimum weight for block C in order to keep the whole thing not moving? We found that the weight of block C has to be 66 Newton. Okay, just based on this. Okay, and so that's that. So that's your part A. Determine the minimum weight of block C so that the whole thing is not moving. Okay. Now the second part says that block C is suddenly lift off. What is the acceleration block A if mu k is 0.15? All right. So now they change the situation now. So this block is lift off, which means that it's no longer here. Okay. And the mu k is given, which is 0.15, and you're asked to find what is the acceleration. What is the acceleration of block A? Okay, so let's redraw this whole free body diagram. Now that the block C is no longer in existence, so you have mu k, which is 0.15. All right, so if it's the case, how many forces acting on block A? So you have weight, block A, that's weight. You have tension, okay, and you have the upward normal force. And then we have to assume that it's moving in what direction. So let's say it is moving. Let's say if we assume that it's moving in this direction. If it's moving in that direction, which means that the frictional force, which is the kinetic friction, has to be in the opposite direction. So that's your Fk. So from this diagram, we can actually find out what is the acceleration. So we can solve equations. So vertically, normal force is just equal to Wa. That's simple. Okay. Horizontally, you have tension minus Fk, and that has to be equal to the mass of block A times the acceleration. This is the net force in the horizontal direction. Friction tension minus friction, that's equal to the mass of A times the acceleration. Now, if the whole thing is assuming moving rightward, which means that block B is moving downward, so you can write that equation. So the free body diagram, you have B and you have the tension. So if it's moving downward, which means that WB minus tension is equal to mass of block B and then times the acceleration. So again, this is a two-body system. You have two equations, two unknown, add them together, the tension gets eliminated. So when you add that, you have the weight of B minus the frictional force on block A, that's equal to the total mass of the system, and then times the acceleration. So in that case, WB is 22, and the frictional force, which is Fk, your Fk, it should be mu k times the normal force. Your mu k is 0.15. And then your m value is the weight of the block A. So you have this simple equation, and then the mass A and B. So you have 44 plus 22, and then divided by 9.8. Okay. So when you do that, you should get a value that says 2.28 meter per second. And this is, your A value is a positive value. It means that, it is in the same direction. The motion is in the same direction as we assume, because we assume that it is moving rightward. Now, if you assume that the motion is leftward, then after you go through the calculation, you'll find that your acceleration will get a negative value. It just simply means that the motion is in the opposite direction of what you assumed. Okay, so that's basically that. Okay, let's go to stop here.